Hi everyone, this is a video for the Oxford Online Maths Club revisiting some curve sketching. I've got Deepak back on the
Hi guys.
stream, and we're going to sketch some of the curves that have been turning up at the end of the further reading each week. Let's get right to it with the first one, which is y equals sine of e to the minus x. Let me draw some axes. This is a classic one of my curve sketching questions where I smash together a function inside a function. What do you think about this one, Deepak?
It's already looking a bit weird, and what you will find is when you find sorts of compound functions where you're sticking functions inside of other functions, all sorts of weird stuff happens, right? But something very sort of specific happens when you do sine of a different function, right? Because sine is always stuck between -1 and 1, right? So we already know we could already draw a sort of a 1 and a -1 because we know whatever we do, whatever e to the minus x ends up being, it will sine of it will always be between -1 and 1. So that's always something to think about. Right. I think we'll start by sketching it for x bigger than 0 or x bigger than or equal to 0. And even if I don't really know anything about the thing, we can immediately just sort of think, let's just put on some nice points, right? So x equals 0. Oh, this is actually not as nice as a point as I thought it'd be, because that would just be sine of e to the -0, right? So that's just e to the 0, which is just 1. So sine of 1. So that's actually not a nice point, but at least the sine of 1 is going to be somewhere between 0 and 1, right? We'll keep that in mind. That did not turn out to be a very nice point at all, right? Okay, I guess I'm going to go on a bit of a tangent about sine of a function, right? Let's take a look at sine of 2x. Let's put a k. I feel like I'm going to start going on a bit of a tangent here, right? And now if you start thinking about this for different values of k, right, you'll notice that as k gets bigger, right, it sort of looks like a sine wave, but oh my god, that never happened. So this is just sine of x, right? And I'm scared of running out of space here. We draw another axis. If we decide to draw like sine of 10x, for example, it's sort of the same. Ooh. I'm not very great with, as you can tell, not an amazing sine curve. It's sort of the same thing, but sort of compressed a bit more, right? So sometimes, if you're a physics guy or whatever, you'll call this I want to say the frequency, but I'm a little bit scared. Something to do with frequency, something to do with time periods, right?
It's wavelength or something, isn't it, for the
Well, yeah,
K?
it's something like that, right?
It's getting shorter as K
Yeah,
gets
I think it might be frequency,
bigger.
but I think it's frequency divided by 2 pi, maybe something like that, or 2 pi times frequency. But the idea is that if it gets much bigger, it's sort of the sine waves get closer and closer and closer, right? This will make a lot more sense when we start talking about what the graph actually is as well, right? So now let's just consider, well, what's even going on with e to the minus x, right? Because if that goes really big, we'll have an idea that the sine of that function will start sort of getting really close together. And you'll notice this, we've barely done any calculations. We're thinking solely about how these functions behave, and we're already going to be able to deduce loads of interesting stuff about this function. So we'll just do a quick sort of like mini sketch, I'm going to call it, of e to the minus x, right? E to the minus x, I think, is just a weird way of writing 1 over e to the x, right? Right, as of now, we'll just consider x bigger than 0, right? And in a way, this is also a composite function, right? Because this is 1 over a function, 1 over e to the x, right? So now let's have a think about e to the x, right? Let's go even deeper, right? E to the x, pretty classic. It just gets bigger and bigger and bigger and bigger, right? And 1 over something, as something gets bigger and bigger and bigger and bigger, 1 over that will just get smaller and smaller and smaller. And this, you'll see this, because if I just quickly do a sketch of 1 over x, right? As it gets further to the right, it gets lower and lower down, right? So this 1 over e to the x, loosely, right? I'm not even going to try. So x equals 0, this is going to equal 1. And it's sort of just going to go further and further, lower and lower down, but it will never ever reach 0, right? Because we're dividing by something bigger and bigger and bigger, but it never reaches 0, right? So this will sort of look like a 1 over x, but technically like a lot steeper, right? Because that's if you think about derivatives, but I feel like I'm going a bit of a tangent, right? So now we already know that 1 over e to the x, or e to the minus x, will get smaller and smaller and smaller as we go along, right? And bearing in mind what we've said about this sine of kx, right? since it's getting smaller and smaller and smaller, right? That's going to correspond to this graph, sort of the sine waves being more and more spread out, right? So we have a loose intuition, a very loose intuition about what's going to happen, right? Now, now what we can start doing is actually start some calculations, and we can actually see if our intuition's right, right? That's something that should be quite good. So it's not immediately obvious. So we have a rough idea of it, but I think to get some nice points, we should probably end up finding some turning points or something like that. So let's have a go at differentiating this sine of e to the minus x, right? So this is going to be a chain rule sort of thing, right? So if you've not seen this, unlucky, I guess. So, I don't know.
We did the chain rule on one of the episodes of the live stream. I'll check the episode number and put a link in the description if you want.
Just
to
in case, watch that one before this one.
Makes this your lucky day.
So this will end up as cos of e to the minus x times by the derivative of the inside function, which is going to be e to the minus x, which is just going to be e to the minus x times by the derivative again of the inside function, which is just going to be minus 1. Right, and then for the turning points, we could actually consider the behavior of this as well, but this is a horrendous function, so we're not going to do that. But for some functions, like sometimes you'll have functions as they tend to, if your derivative will tend to infinity, you'll notice it gets more and more. I just realized I'm reflected in the camera. It'll get more and more sort of steep, right? And if it tends to 0, it'll get like flatter and flatter and flatter as you go through. But in this case, it's not very helpful, right? But if we're interested in when this is equal to 0, well, e to the minus x is certainly not equal to 0, so let's just bin that, right? And then it's going to be, well, when is cos of e to the minus x equal to 0? Well, we can inverse cos both sides sort of thing, e to the minus x. And cos is 0 at every sort of quarter pi, I don't even know how to say it. So, for example, it's pi by 2
3
plus...
pi by 2, 5 pi by 2, and so on, isn't
3
it?
pi by 2.
Odd multiples of pi by 2, I think is how I would say it.
Yeah. I don't know why I would say it.
I guess that's where, I guess if cosine is 0 there, it's where sine is 1 or minus 1. And that makes sense because it's your sine function on the outside hitting its maximum or minimum at 1 or minus 1. That's where the turning points line up. It's nice that works out like that. Sorry, I was interrupting you. E to the minus x equals pi by 2, 3 pi by 2, and some other
5
stuff.
pi by 2. We could write this as e to the x will equal 2 by pi, 2 by 3 pi, and so on, 2 by 5 pi. I don't know if I put so on. I've written another one. But if we ln both of them, one of the sort of consequences of that is we're going to find the x value. Yeah, I'm straight a bit off here.
Okay.
The x value is going to just be further and further spread out, right? Because these are, and that sort of checks with our intuition about the actual, because when we were thinking about the derivative, right, we were thinking as x, we weren't thinking about the derivative, we were just thinking about the function, right? As x goes really big, this is going to go really small, which should give us some bigger wavelengths, right? And since it's getting bigger, the turning points should be further away, right? I'm scared I've just come to an incorrect... Is it a right conclusion?
So all of these numbers as well, I'll give you another observation for free. All of these numbers are less than 1. Kind of because the first one is less than 1. So you've got these values of e to the x that are all less than 1. I think that means that they all correspond to values where x is less than 0. Because of how e to the x is bigger than 1 when x is bigger than 0, and it's less than 1 when x is less than 0. So I think what you've shown is that all the turning points... Oh, I'm going to write this very slowly. All the turning points are on the left for x less than 0. So maybe we should have... You saw the value before. At 0, it was sine of 1 or something. And then after that, no more turning points. So it's just gonna be nice afterwards.
Right,
Should we try and sketch this?
I think we can have a go. I've just realised the whole intuition thing I have relates to the graph to the part we're not even sketching. So
We might sketch
but
x negative as well. I might get you
yeah,
to do x
it
negative
won't
as
be
well.
it won't be nice. It definitely won't be nice. Right, but we have a go. So sine of 1, we know it's 1 is less than it's between, I'm not even gonna. So pi by 2 is about 1.5. So it's
Yep.
between pi by 4 and pi by 2. So it's bigger than root 2 over 2, but less than 1.
It's quite
Right?
big then. Okay.
Quite fairly big. That's what I'm trying to get to. So it's more than, well, it's going to be root 2. 1 over root 2 is root 2 over 2. Root 2 is about 1.4. Divided by 2 is about 0.7. So it's definitely bigger than 0.7. Right? So quite big, quite big. So I'm just going to draw it sort of here. Right? And now the thing is, I'm scared I'm going to butcher this. So the things to remember, there's no turning point for x bigger than 0, right?
Yeah.
And it's bounded between 1 and -1, right? It might just be worth plugging in whether this is plugging in x equals 0 to see how it's going to be slanted at 0. It's just because I'm a little bit scared if it's going to be increasing or decreasing, or maybe there's a deduction I'm missing.
Well,
right.
I've got a different angle. We could plug 0 into
Okay.
the derivative thing. For the people who haven't seen the chain rule episode, let's say, what happens when x is really large? Because there's no turning points, it kind of feels like it can only do one thing between here and infinity, right? So I'm keen to look over at infinity. When x is really huge, e to the minus x, that's like 0, right? So I think when x is huge, this is going to be like sine of 0. It's going to be like 0.
So it's going to approach 0. This is always a tip I give to people sketching graphs, and I didn't even use it, right? But always consider what happens. So really big, really small, x equals 0, things like that. But yeah, if you imagine this is going to be going somewhere towards 0, right? And there's no turning point at all, this cannot start going up, because if it starts going up, it's going to have to turn sort of back down, right, to go back to 0. But that will imply there's a turning point, right? So that is clearly wrong. So this must sort of just be going a little bit like sort of, this should be getting smaller and smaller. That is not very good. But that, I feel like that's more from the
Good enough. It's coming down and flattening out.
it's going. It's my hands shaking. That's the thing. I might have another go at it. In fact, no. I think we'll leave it, or we'll have James. So
I might draw over the top of it. Okay.
Yeah.
Oh, right. Okay. Yeah. Down to 0, right?
Yeah. But never touch a 0. That's where my hand.
All the turning points are over here. That's what you proved for
Yeah.
the derivative. All the turning points are for negative x values. So there's one just over here, I think.
Yeah.
And then I'll do the left bit. You've done the right bit.
Go on.
So then there's another turning point down here, and the turning points get closer and closer together because I suppose e to the minus x, as I go left, minus x is becoming a bigger and bigger number. So e to the minus x is becoming bigger and bigger and bigger. So the thing's quickly going through, the values rushing through numbers exponentially fast. We're plugging all those numbers into sine, so we're running through values of sine faster and faster and faster until you sort of have this bit over here.
Until Desmos breaks, usually.
Yeah.
I believe you explained it so much better than me. I tried to go at the sort of physics angle with this is like the frequency, the more it goes through, but your explanation...
Oh no, I like the frequency. I like the frequency thing as well, because this is on the left there, where there's lots of turning points, and it's going through sine values really fast. That is a high frequency bit of the graph. I think it's a good way of looking at it. In fact, it's where this graph came from, because I came up with this graph while I was thinking about what the waveform for a kind of slide in music between two notes would look like. So if you're sliding between two notes, you want to change the frequency in between, and kind of the way frequency works for different notes in music is kind of exponential. You might know that an octave is what happens when you double the frequency. So there's this kind of exponential thing going on with frequency. So I thought, hey, let's put an exponential inside a sine, and then that'll have the frequency changing sort of exponentially, which is the right sort of thing that you want for different notes. So this is a sort of bass drop in curve sketching form. Right. Hi, so after recording with Deepak, I went away and coded up the bass drop in Python. My Python code is really bad, don't at me. All this is doing is setting up some variables and then working out sine of exponential of minus time. Because all of the action was over on x negative, I've translated the curve over into x positive just a little bit. That's equivalent to multiplying by some factor inside the sine, but not inside the exponential. I've picked 440 times tau so that it starts on a nice consonant note. That makes the graph on the right, and it makes a sound like this. Nice. Okay, next one. I've got y equals, and then some horrible powers of a over x. So a over x to the power of 12 minus a over x to the power of 6. What do you think
Right.
about that one?
Graph number 2. I will not lie when I say that does look abhorrent, to be fair. You've got, not only have you got 1 over x's, which tend to do horrible things at x equals 0, you've also got powers of 12. And powers of 12, that's not something you see in A level. It's not something you really see until you get to real life, right? So this is already looking a little bit strange. And with gigantic powers and things, all sorts of weird stuff happens. Like, I can promise you, many of the people watching this will have played with Desmos, like x to the power of a, and just slid a really high just to see what happens. And you already know stuff starts getting very strange, right? High powers of stuff, as you can imagine, the derivatives also weird behavior, so they all just end up doing weird things. But let's have a look at what's going on in this graph, right? So x bigger than 0. Hopefully I don't make too many deductions about x less than 0 like last time. But so I guess the first interesting point is going to be near x equals 0, right? Obviously x equals 0, it blasts off somewhere, something. Anytime you have divided by 0, it ends the world, right? So you can't do that. But the way I guess to think about what's happening near x equals 0 is, well, if you just imagine 1 over x, right? As x gets smaller and smaller, oh, you can't even see my 1 over there. 1 over x, well, if you imagine x getting smaller and smaller and smaller, you're sort of 1 over, like a smaller thing, I guess you could say 1 over like k, right? And if you imagine k getting bigger and bigger and bigger, right? And then you 1 over it, it starts getting bigger and bigger and bigger, right? Because basically, if k goes big, then the number's going smaller. This isn't a very good analogy now I'm thinking about it. But as k goes bigger, and then if you imagine that's actually the number going smaller and you 1 over it, it's actually getting really big. But then the thing is, as k gets to sort of infinity, or which would be the equivalent of going to 0, well, 1 over it just blasts off to infinity. So it goes absolutely insane, right? And then you might think here, well, now there's 2 of them and they have different signs. And in a way, this is a sort of battle of the 1 over x's, right? There's sort of one that's going really, really, really big in the x equals 0, right? And another one that's also going really, really big, but it's subtracting from it, right? But the important thing to notice here is that this is to the power of 12, right? So something going smaller and smaller, something go bigger and bigger and bigger when you do it to the power of 12 is going to be way, 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 way bigger than the same thing to the power of 6, right? So it's still going to be gigantically huge, right? And by this logic, we know it's going to approach infinity, right? Because this is taken away from it, this right thing on the right, and it is also huge, but it's literally orders of magnitude smaller. And I'm literally using that in a literal sense. Literally orders, it's literally the square of it, right?
So when x is near 0, this is, I think you've said, really, really positive and really, really, really big. I guess that gives us this bit of sketch.
Yeah.
Over here. What else can we say about this?
Yeah, so it's already looking like 1 over x. And then another thing that, as we've done before, as I forgot to do before, we might want to consider, well, what happens when x gets really, really big, right? And then these being 1 over x functions, you can sort of, this 1 over k analogy does not really work. But as you can imagine, 1 over x, as x gets really big, it's fairly common knowledge, it just gets very, very small, right? And it's the same thing, these things are taken away from each other, but it doesn't really matter because both of them are going to 0. And since you're subtracting them, eventually it's just going to be something close to 0, subtract something close to 0. As long as you're far enough down, you'll be close enough to 0, right? sounds a bit. That's already sounding a bit real analysis-y, but don't worry about it. Basically, it's going to go to 0 because both of them go to 0. Why wouldn't it? So we know eventually it's going to be going to 0, right? And then the question, you could also ask whether it's going to be coming from above or below, right?
Yeah.
I think this is quite a hard deduction now, because then it's the question of, well, which of these a over x to the power 12 or a over x to the power 6? I really like this question. It's like these two gigantic powers of 1 over x battling each other, right? So so if you imagine x getting really big, or specifically x bigger than a, right? But we're considering x going super close to infinity, right? Is certainly bigger than a, right? This a over x is going to be less than 1, right? This is less than 1, and this is also going to be less than 1, right? And then now, if we ever think about something that's less than 1, if we take it to the power of something less than 1, so let's say we can just play around with this. Sometimes if you don't know how stuff's going to behave, play around with it. So let's take a look at a half, right? If we square that, it's going to go to 1 over 4, right? And the observation I'm trying to say here is 1 over 4 is smaller than 1 over 2, right? So as we get x going bigger and bigger and bigger, we'll have something small to the power of 12 subtract something small to the power of 6. But what we've shown, or sort of thought about, is that numbers less than between 0 and 1, if we make them to the power of something bigger, they actually get smaller, right? So a over x, for x bigger than a over x to the 12 will be less than a over x to the 6, right? And that's a very, very fancy way of saying this function will be less than 0 as you get really far on. That's quite a hard deduction to make, and what you'll probably find is it might actually end up being unnecessary in the next bit, right? So we know it's probably going to approach, it will approach from below, right? So it's going to do something like that. I don't know. We don't know for certain, right? But something like that. And then I guess the question is, well, what goes on in between? I don't know. You could try all sorts. You could maybe plug in certain numbers and things, but I think, as usual, as for tradition in graph sketching at this point, I think we're going to have a go at differentiating and seeing if there's any turning points, because there's no guarantee there even will be, or even for x bigger than 0. But let's have a go at differentiating. So these are just polynomials and things. So they're not very nice polynomials, but they are polynomials. So this will get us minus 12 a to the 12 over x to the 13. I'm sort of splitting these, but it won't matter too much. And then this will be plus a to the 6 over 6a to the 6 over, my a's don't look very a, but that always happens.
That's the only
divided by
other than x. X to the 7 down here, yeah.
X to the 7, yeah. And then we're just going to say, well, let's just set that equal to 0, because we're after turning points. Right, I'm scared I'm going a bit off screen. Wait, that is the right derivative. Right, yeah, I'm scared I'm going to tank this.
I think so. So you've thought of a over x to the power of 12 as a to the 12 over x to the 12, and then that's a to the 12, x to the minus 12. You can differentiate that, and similarly for the other term as well.
A to the 12 is just a constant. I mean, it looks horrible, but completely differentiable. Yeah. I guess we could write this as 6a to the 6 over x to the 7. I'll keep them going off screen.
Yeah, it's fine.
Equals 12a to the 12 over x to the 13. And then we could times by x to the 13, which isn't particularly nice, but it gets you 6a to the 6 times by x to the 13 minus 7, which is 6, hopefully, equals 12a to the 12. Right, my a's really look like 9. It's not great. And then we could divide by 6a to the 6. That gives me x to the 6 equals 2a to the 6. Right, and then this gets us something that doesn't look very nice, but for our purposes should be okay. So it's going to be the 6th root of 2, which is certainly not something you see in everyday life, times by a, right? And I guess this begs the question, what even is a? Is it positive? Is it negative? Or
a in this question, a is some positive number. Yeah, I should have said a is some positive.
Yeah. A is some positive number, right? Because that's gonna That's going to affect wherever the turning point is, right? But
Sure.
a is bigger than 0, right? So the sixth root of 2 over a, well, it's going to be somewhere in there, right? We know there is a turning point, right? Let's just see what happens if we plug that in, right? Because this is our turning point. That'll tell us whether maybe it's super high up, maybe it's super low, maybe it's literally on the axis. Who knows? Right, let's try plugging in x equals the sixth root of 2a, right? So y is equal to a over x, and then x is going to be the sixth root of 2 times by a to the 12. Luckily, these a's cancel, so this isn't actually as bad as I thought it would be. A over sixth root of 2 again, and it's a's cancel again to the power of 6. So this is 2 to the minus 1 over 6. Absolutely nothing happened there. I'm hoping this gets edited. Subtract, there's going to be 2 to the minus 1 over 6 to the 6th, right? And then we just use the sort of indices product rule. You've all seen it before, to get 2 to the minus 2 subtract 2 to the minus 1, right? This doesn't look very nice.
It's lovely.
Yeah, considering this function is powers of 12, that is, to be honest, that has blown my mind a little bit. I really wasn't expecting it to be that nice. I was expecting more deductions or something. Well, and this is just 1 over 4 subtract 1 over 2, which is literally minus 1 over 2, which is the answer you could only dream of when graph sketching. But so,
1 over 4, but yeah, 1 over 4, but yeah.
1 over 4.
It's negative is the point. Cool, right, okay, let's put it on. Let's scroll up here.
Right.
Put it on.
Right. So this is x equals sixth root of 2 over a. The axes, because this is really the only nice point we can draw. We can just kind of say we've scaled the axes secretly. But let's just say, let's just throw this is going to be x. There's going to be some point which is positive, which is going to be the sixth root of 2. That's by a. And we know it's going to be minus 1 over 4, right? So it's going to be somewhere like here-ish, right? And this is already working with our previous intuition, right? Because we knew it was going to approach infinity from below, right? So this is already looking, as you can imagine now, it's almost a sense of connecting the dots, right? So we have something like blowing up, and then it slows down. There's a turning point. There's only one turning point, and then it will slowly approach minus 0, 0 as it approaches infinity.
Looks good.
How's that looking? Good?
Yeah. I really like this because it's like the thing you said about the two different powers. They're both massive and scary powers. They're kind of fighting each other. And it's the first term, the a over x to the 12, that wins over here when x is small. And it's the other one, the a over x to the 6, that wins over here when x is really large. In between, there's this kind of turning point somewhere. And this point where it crosses the axes as well. I reckon, by the way, I think this point might be. I've got a feeling this is A.
Oh yeah. You could solve that.
Then they're both
They'd
one.
Be one. Yeah. That is
nice.
That is something we.
And this is a function that blows up near 0. It decays for large x, and it has one turning point. This is called the Leonard-Jones potential. Let's see if I can spell Leonard-Jones potential, and let's then see if I can explain the Leonard-Jones potential. It's a model for atom interactions. So if you've got something like gravity or electrostatics, the atoms might just attract each other or might just repel each other. But in real life, chemistry is a bit more complicated than that. There are multiple forces that might be playing a role. And some of those forces might be more important on short distances, and some forces might be more important on large distances, which is what this is sort of an analogy for. It's got these two competing forces going on. So then the minimum that you found is relevant in Leonard-Jones potential world because it's a sort of equilibrium distance that particles in this model might happily stay at that distance. So nothing like gravity. Gravity says wherever you are, you're going to fall towards things in gravity. If you've got a potential like this, then the two forces can be in sort of perfect balance at a particular distance. And you get atoms forming these nice structures where things are at the right distance. Leonard-Jones potential. Links in the description.
Sadly, the real life is usually not very mathematically nice. If it's mathematically nice, it's usually wrong.
Okay, one more. I've got when x is bigger than 0, I've got y equals natural log of x over x, which I've written as ln x, but I know that some people write it as log base e of x, and I know
Log
that some
base e.
people write it as log x, but I've written ln x in this.
Yeah, that's weird notation actually, because when I see log, I assume that means log base 10, which I think slightly weird. But yeah, so this graph is already, it's something you do see often. I feel like when people make graph sketching exercises and they're a bit lazy, they will just divide a different function by x or times a different function by x. It happens. But I guarantee you this example is actually very interesting. But you have to sort of think a bit more. But already, I guess with kind of some intuition, well, as ln of x, as x gets really big, ln of x will also get really big, right? Not amazingly fast, but yeah. It gets bigger and bigger and bigger, but not amazingly fast, right?
Yeah,
And
not
then
as
this
big
divide,
as x, for example, right?
yeah, that's the idea I'm trying to get at. X is way quicker, right? And you can see this if you graph this on Desmos, your x will go well above ln x, basically immediately, right? And the idea is that for very big x, this x is gonna sort of beat out this ln of x, right? And you're gonna sort of, as it gets really, really big, little side sketch from Jane, x gets way bigger, right? So this is gonna be a sort of denominator where the bottom is way, way, way bigger than the top, right? So it must necessarily approach 0, right? And on the same topic last time, we know this one's going to be approaching it from above, right? Because for big enough x is bigger than 0, because, definitely is, we're talking about big, and ln of x is also, because e to the power of what is something really big, provided that number is bigger than e, that's certainly going to be positive, right? I mean, it's all, yeah. Right, so we know it's somewhere it's going to do something like that, right? It's gonna go like down. Another thing we want to sort of think about as well is what's going to be happening at obviously not the exact point x equals 0, or whether it blows up, or maybe because you get weird examples like sine x over x, it just somehow it sort of feels like they sort of cancel out when x equals 0. Like if you graph sine of x over x at x equals 0, despite there being an x at the bottom and it looks like it's going to explode, it doesn't. It literally just goes to 1. So with this graph, we can sort of use similar reasoning, but we need to think quite a bit harder about what happens near x equals 0, right? So one thing I think we'll go a little bit earlier this time. I think we'll differentiate a little bit earlier, because I can already imagine thinking about graphs near x equals 0, it's going to get a bit messy, and I might like some extra time in my head for that. So let's figure out what the derivative is, right? This one's not too bad, nothing chain ruly. This will either be the product rule or the what is it called, the quotient rule, depending on how you like to see it. I'm myself very much a product rule guy, so to say. Minus ln x over x squared, and then this is quite nice because they actually end up having the same denominator, right? So this is 1 minus ln of x over x squared.
If you're going to put it over a common denominator, it feels like we should have used the quotient rule. I'm going to speak up for the quotient rule now.
I don't know. I think just when it came up, I really remember it coming in my lesson, and they showed us the product rule, and then they were like, well, here's the quotient rule. And in my head, I just thought, well, obviously, you've just showed us the product rule. And then since then, I've always been stubborn, right?
Okay. So the quotient rule does follow from the product rule.
Yeah, but I don't know. Yeah, I guess it doesn't really matter. I guess one thing to notice is that, well, if we consider when this equals 0, it does have a turning point, right? And it's quite a weird turning point, right? At x equals e, this has a turning point, right?
Oh yeah. When ln x is 1, this has got
right.
Yeah, this
so
is 0.
X like e to the power of what is e is 1, right? That's probably a weirder way of wording it. But let's say, I don't know, e is about here. It's going to be a bit of a weird scale. We know there's a turning point, right? What you could do, right, is we don't know if this is going to be above or below. Well, you can actually, we'll just plug this in to know if it's above or below, right? Because you don't really know. Like, you can probably make some clever deductions, right? Let's just plug in x equals e. You get y equals ln of e, which is 1, and then divided by x, which is e, right? Which we know is going to be positive, at least, right? So it's going to be somewhere like I'll just say here. We'll play connect the dots later, right? And now the weird question is, well, what's going to happen as we get close to x equals 0? And I'm a little bit hesitant here, so I'm not using too much harder maths.
I'll give you a clue.
Right.
It's not like your sine x over x example. In your sine x
Yeah.
over x example, that's a sort of careful balance because sine x is getting close to 0. Also, 1 over x is a bit bad. So it's this kind of force between sine x being well behaved and 1 over x being badly behaved in that sine x over x example. This one's not like that because it's log x, which is badly behaved, multiplies by 1 over x, which is badly behaved.
Right. So I'm just trying to think. I don't want to resort to anything too high mathsy.
Yeah,
I guess
it's just really bad, right? Log
I
x.
guess you could sort of reason like purely say ln is also approaches but worse. I don't know.
Yeah, it's sort of like, I guess I would say it as like ln x on the top there is going to minus infinity as x gets close to 0, and 1 over x is getting really big. So we have something that's a bit like minus infinity multiplied by something that's a bit like positive infinity. Okay, maybe I shouldn't say infinity in there, but it is what I think in my head.
Yeah.
So that thing's going to be negative, and it's going to be huge.
Yeah, it's certainly going to be negative as well, because if you think near x, always with ln, things, because we're considering x very close to 0, x is certainly going to be less than e, isn't it? So ln of x will be negative, whereas x will still be positive because it's just close, because we're only thinking about x equals 0. So you could have always deduced, but I think you want to be careful when saying things like infinity times infinity, but we know what you're saying. You know what I mean? I feel like any interviewer or whatever will know what you're sort of saying, but sometimes they don't like it. So it will certainly be negative, and it will certainly be approaching infinity, right? So if we can,
right?
Yeah.
Like
Yeah. Oh, do you want to have a go? You can sketch this
Can
one.
I sketch this
I feel like I'm.
Oh yeah.
I feel like I'm hogging all of them.
I'm going to change colour for it and everything. So it's over here. It's not infinity, but when x is a little bit positive, this is negative large number divided by tiny thing, and when you divide by tiny things, things get even bigger. So this is really negative over here. It comes up. I think it goes through 0 at some point. Maybe we should think about that point because I've got to get up to this dot, haven't I? And then it's probably smooth through there. And it's got this turning point at E, and then after that, it's downhill from there. I kind of know that it's downhill from there because you found all of the turning points over here.
Yeah. Certainly, and we know it approaches 0 as x gets like really, really big.
Yeah, so it's going to calm down after that. It's got this maximum at E, 1 over E. What do you think this point is? Where it goes through, crosses the x-axis? If you want to make this feel like an interview.
Well, I guess it's going to be, y is going to be 0, so ln x over x is 0. So I already feel like something weird's happening because ln x equals 0. Well, it'll just be e to the 0. So if we e both sides of, let me just write out what I'm saying.
Yeah.
So y is 0, which is ln x over x, right? And then we're not bothered about the bottom. So this is just whenever ln x equals 0.
Yep.
And if we e both sides, you get x equals e to the 0, which is just 1, which is quite nice, actually, considering. But to be fair, we didn't even think about that, and it came out just through the other. I have a habit of doing this with graph sketching, not considering roots, because usually when I sketch stuff, it's horrible stuff that doesn't even have roots, right? So
we've had the sine of e to the minus x one had some horrible roots that I really didn't want to try and work out that all involved logarithms of fractions involving pi. The previous one and this one have turned out to have quite nice places where they cross the axes. So we get this nice graph like this. It's super badly behaved at 0, really not very nicely behaved over there. But then it comes up and goes through some nice points like this.
Yes, we talk about why it's interesting. Well, I guess what if we talk about an absolutely classic interview question, right? Or something that you might see in a YouTube video, depending on how mathsy your YouTube recommended is, right? You might say, well, what is bigger, right? Is it going to be pi to the e or e to the pi, right? And this immediately is already a slightly weird question, right? Because they're already pretty close. Pi is a bit bigger than 3, e is a little bit less, and you've got something smaller to a bigger power, or you've got something bigger to a smaller power, right? And you can imagine, you might be able to see where I'm already going with this, right? you might just be considering like, how does this relate to this graph ln, and you can already see where this is probably going to go, right? But if let's just do something interesting. Let's just consider the general case, right? Let's consider, is a to the b bigger, when is a to the b bigger than b to the a, right? And then now I'm going to ln both sides, as you can imagine, a bit of my hint, right? But you should actually be very, very, very careful when you're lning certain inequalities, right? Because ln is an increasing function, right? So it will, a fancy way of saying it, sort of preserve the inequality, right? But if I do this, if I imagine like, you can't sine both sides of an inequality because there's no guarantee that will work, right? Because sine is increasing in certain parts and decreasing in certain parts. So we should really check, well, if we have something that's bigger than something and we ln it, and if we compare it to something smaller than it and we ln it, will it work? In this case, with the function ln, it works. But you should have a think that there's always stuff you should be worrying about inequalities. My top list of worries with inequalities are lning things, or let's say applying functions, right? Or multiplying by x, right? Multiplying by x is a sneaky one, right? But if you multiply by x and your x is less than 0, you're flipping the inequality, right? If you ask anyone what happens to an inequality when you times it by a negative thing, they'll happily say, oh, inequality flips. But times it by x is really sneaky. But little hint, multiply by x squared instead. That'll save you a lot of time, right? Any other weird stuff to look out for in inequalities? Maybe strict stuff, but I don't think you'll really see stuff like that at A level, or hopefully you don't, because otherwise you'll be doing some brutal maths. Anyway, tangent over, right? so I don't know if you've seen, I'm hoping you've seen ln rules, but the idea is that if you have ln of a to the power of something, you can sort of pull out this this thing, right? And this will be a to the ln b. And now you can probably see, if you hadn't spotted before why we're going to be using ln x over x, you will now, right? So one way of writing this would be ln a over a. Remember, we're considering, let's just consider a and b bigger than 0. But I said the whole thing with be careful when things aren't positive, but it's most of the time it won't matter. But if an interviewer is trying to be sneaky, maybe. True story happened to me. And you get ln a over a versus ln b over b, right? And then let's just have a quick look at this function, right? Right, if we've considered ln x over x, right? And then we're thinking, well, when is something bigger than something, right? And what you'll notice is, as things get really big, the ln x over x goes to 0, right? Or as you get close to 0, it blasts off to minus infinity. So this is still sort of very dependent on what a and b really are, right? But as you might have noticed, I have a very, very specific example here. A very specific example, almost pre-chosen, as one of the reasons we sketched this graph, right?
Almost like we planned this.
Right. Because what you notice, this function, ln x over x, the turning point is at e, right? So regardless of whatever ln of whatever over whatever, if you choose a to equal e, this will be bigger than anything else you throw. So not only is ln ln x x equals e, ln x over x will be bigger than anything, provided your ln thing is not, like, if you're asking about positive things, which we certainly are with the e versus pi versus e, right? So we know, well, pi to the power e, right? Well, we can sort of do this now backwards, right? We know if a is equal to e, this is certainly true, right? And then we sort of reverse our working back, right? And then you set b equal to pi, right? And we know that pi is not the unique maximum, right? So this inequality works, right? Just put a tick. And then we just work backwards, right? And then we end up with our original statement. E to the pi is bigger than pi to the e, right? Which I think a surprisingly cool way of doing the question, right? Because who would even think of this graph? And I think you'll come up across with this in maths, where something happens in an example, right? And then they call it pulling something out of a hat, right? They're like, consider this insane function, and something just happens to happen, right? Usually means someone's put a lot of thought into something, right? But it can seem very mysterious. I remember feeling very puzzled by things like this, but it's a cool example nonetheless.
Yeah, I love it. So e to the pi is bigger. I've got another item for your list, of course. So applying functions to inequalities is dangerous and scary. Multiplying by x is dangerous and scary. I'm going to add reversing.
yeah.
Reversing is dangerous and scary, and we just did some. So I guess
Yeah.
homework is to check that e to the pi really is bigger than pi to the e by checking that you can reverse all the logic here to get back from. So I guess starting from the fact that log e over e, which is 1 over e, is bigger than log x over x for all other positive x. So starting from there, you work back to the fact that e to the pi is bigger than pi to the e. And there's a homework problem as well, which is to think about positive integers. So what if I say that the numbers have to be whole numbers? And I was thinking about this question that led me to this curve in the first place. If I've got positive whole numbers a and b, so different now because I'm saying they have to be whole numbers, when is a to the b equal to b to the a? So there's some easy solutions. If a and b are the same number, then a to the b is the same as b to the a. But there are some other interesting examples as well where a is not b.
Can I suggest the homework problem?
Yeah,
just
absolutely.
on this whole idea of inequalities. Bearing in mind some of the stuff we just said here, something interesting. This is quite a classic problem, which if you apply to Cambridge, I guarantee you will see this question. So sorry for spoiling it, but it's a really nice question. So it's 1 plus 2x minus x squared is bigger than 2 over x, and we're not considering x equal to 0 because that breaks it, right? It's just bearing in mind the things we've said about inequalities, some interesting things happen. But yeah, I think that's a cool problem.
Oh, this is a past step question, isn't it?
Yeah, this is from the
question
sick class booklet. Yeah, this is a sick class booklet.
Okay.
This is classic stuff.
So there's a step, and the idea is that you solve for when does this happen, which values of x is true. It's not always
question.
True, is it? Or maybe it is. Maybe that's the question.
Okay. No spoilers.
No spoilers, right? Okay. Great stuff. That's all the curve sketching for today. Thanks for coming on the show, Deepak.
Thanks for having me.
Been great fun. Season 2 of the live streams for Oxford Online Maths Club start again on the 22nd of April, so we'll see people around then, I suppose. Take care, everyone.